The Floyd-Warshall algorithm finds the shortest route between 2 points. So suppose we have the set of direct distances labelled CIK from city I to city K for all cities 1 up to n. We can display these distances on an n by n matrix, which we will label C. So C will have the entries C11, C12 up to C1n, C21, C22 up to C2n, and down to CN1, CN2, sorry, it's 2, all the way across to CNN. So this is our direct distance matrix. For the diagonal entries, this is the direct distance from a city to itself. We set this initially to infinity. This is so that it is possible to find some feasible route which starts and ends at the same city but passes through some intermediate cities. Note that when we say intermediate cities, we mean the cities on the path from I to K, not including I or K. What we want to end up with is a direct distance matrix which we will label D, and this has entries D11, D12, D1n, DN1 across to DNN. So this is a shortest distance matrix. The entries DIK represents the shortest distance from I to K so far. This is because at each stage of the algorithm we update our value for DIK and create a new matrix with these updated values. We then run the same algorithm on this new matrix. Our last point before we move on to the proof of correctness is to define what we mean by a triangle operation. So, a triangle operation for a fixed node J is the minimum between DIK and DIJ plus DJK, and we set this equal to DIK. We run this operation for all J 1 up to n, where J is not equal to I or K. What this operation does is it chooses the minimum distance between the shortest distance from I to K found so far and the sum of the shortest distances from I to J and J to K. If DIK is less than or equal to DIJ plus DJK, then nothing changes and we set DIK equal to DIK. If, however, DIK is strictly greater than DIJ plus DJK, then we set DIJ plus DJK equal to DIK, as this is now the shortest distance we have found so far. The following theorem verifies that the Floyd-Warshall algorithm works, since it verifies that the shortest distance is always found by performing triangle operations for all J distinct from I and K. So the theorem goes as follows. If we perform a triangle operation for successive values J equal to 1 up to n, each entry DIK becomes equal to the length of the shortest path from I to K. So note that at each stage the intermediate nodes must have index at most J0. So first we let J0 equal 1. Then the only intermediate city possible is city 1. Our triangle operation therefore determines the minimum distance out of the two paths DIK and DI1 plus D1K. Step is trivial and it's done for all values of J, fixed I and K. and is then repeated for all pairs I and k. So now assume that the theorem holds for all j equal to j0 minus 1, and consider the case where j0 is equal to j. If the shortest path from I to k with intermediate cities v less than or equal to j0 does not pass through j0, then dik will remain unchanged, as we have this situation. So we have a path from I to k, and it may pass through cities 1, 2, all the way up to j0 minus 1, but it does not pass through j0. And we know this to be minimum by our inductive hypothesis. However, if the shortest path from I to k with the intermediate cities does pass through j0, then our min operation will select the shortest path dij. However, if the shortest path from I to k with intermediate cities v less than or equal to j0 does pass through j0, then our min operation will select dij0 plus dj0k and set this equal to dik. So we have the following situation: I to k with intermediate cities maybe 1, 2, somewhere we have j0, and then after j0 we might have some other cities, let's just say j0 minus 1. By our inductive hypothesis, we know that this part of the journey is at its minimum value, since it has intermediate cities less than j0. The same can be said for this part of the journey, and so both parts of the journey are at minimum distance, and we know the total distance from I to k to be minimum as well. And this completes the proof by the inductive hypothesis.